Okay, so welcome. Today I'm going to continue with the turning performance. So let me quickly remind you what we discussed on Tuesday. So these are the things that we are covering right now: turning flight and the VN diagram. So this VN diagram is an important diagram in aircraft performance. It is also referred to as the flight envelope of an aircraft. And I started with the level turn maneuver. In the level turn maneuver, an aircraft makes a turn in the horizontal plane, and the important, as always, we make some assumptions. First we assume that during the maneuver the altitude of the aircraft does not change, so it keeps maintaining this altitude, and also the speed of the aircraft doesn't change as well. So these are the two assumptions we make for this maneuver, and this is called the sustained level turn maneuver. Okay. Before I started giving you the equations, I explained the difference between a skid to turn and a bank to turn maneuver. If you want to perform a skid to turn maneuver, in that case, the wings of an aircraft stay parallel to the ground, and in that case, the lift force will be perpendicular to the ground. And if to perform such a maneuver, you need a side force to make the turning, and that side force is created using the rudder. So that's how a skid to turn maneuver can be performed. But regular airplanes, conventional aircraft, almost never perform skid to turn maneuver, and the reason is the rudder itself cannot give you large forces. So you can make maybe a very slow maneuver. But if you want to make a real turn, a turn with a reasonable radius of turn, then you need to perform a bank turn maneuver. And in the bank turn maneuver, the wings of an aircraft are tilted. So you basically give the aircraft a roll angle. And so there's an aircraft here, so let me clean up this other stuff. And when you do that, the lift force is tilted. Now the lift force makes a certain angle with respect to the ground, and for the altitude to remain constant, the vertical component of the lift force is now supposed to balance the weight of the aircraft. And since now you have tilted the lift vector, you need to increase the magnitude of the lift vector. So that's an important thing in bank turn maneuver. Okay, so this is a better picture. So now you have this equation for the vertical forces, and the horizontal component of the lift vector is the main force that causes the rotation. Okay, and the horizontal component is lift times the sine of that angle. And that should be equal to the turning acceleration, mass times the turning acceleration, which is v squared over r. So to make the analysis simpler, we define a new variable called the load factor. And load factor is defined as the ratio of the lift force to the weight of the aircraft. Normally during steady level flight, this load factor is 1 because we have lift vector equal to the weight of the aircraft. So this load factor is equal to 1 for a straight flight. But for turning maneuver, since you need to have the lift vector increased, load factor becomes a number greater than 1. So these equations are in your notes, you can study them. So you can obtain this expression for the radius of turn, and then the angular rate during the maneuver is also obtained using that relation, and that equation is also given here. So if you look at these two equations, you will see that load factor is an important parameter there. If you want to make a faster turn, if you want to make a tighter turn, you need the large load factor. Okay, so if this affects the turning performance. And the load factor it's a non-dimensional number, but it is quoted in terms of G's, and the reason for that is shown in this diagram. If you're making a sustained level turn maneuver, then on top of the regular acceleration due to the gravity, there will be a centrifugal acceleration, and their vector sum, which is shown by this vector, is the total acceleration felt by the people inside the aircraft. And if you look at the magnitude of this vector sum, you will find out that it is equal to g times n. So the load factor appears here. So if you are making a turn maneuver with a load factor of 5, then during that maneuver you will experience an acceleration that is 5 times the gravitational acceleration. So that means your body feel like it is 5 times your regular weight. Okay, so if for like a 60 kilogram person, that will be 300 kilograms during a 5G maneuver. Okay, and on Tuesday I told you that this affects the entire design of the aircraft. Okay, so if you want to improve the maneuverability of your aircraft, or in other words, if you want to make the flight envelope larger, which means your aircraft will be able to fly in a wider range of flight conditions, then you need to improve every aspect of your aircraft, not just aerodynamics or not just propulsion systems. Everything needs to be improved, and that's what I was explaining as the last thing on Tuesday. Okay, so today let's consider the C-130 aircraft as an example. You know C-130 aircraft, right? That's a transport aircraft, and it is propelled by 4 propeller engines. So I have the important information regarding that aircraft. W0, the total weight is given as this much, and the wing surface area, the air density, so this is the sea level air density, and I have this data. In fact, I have the actual curves for the lift and drag. So these are the real curves for this C-130 aircraft. So these are the drag polar curves. The vertical axis is the lift coefficient, and the drag coefficient is the horizontal axis. It is hard to read here, but there are 3 curves, and these are for 3 different flap configurations. So this one, for example, so let me mark that. This one corresponds to the clean wing configuration without any flaps. This one corresponds to the condition with flaps extended halfway, which is what you do for takeoff. So it's a takeoff flap configuration. And the last one is the landing configuration, where the flaps are extended fully. Okay, so if you extend the flaps, then the drag polar curve becomes the green one. Without any flaps, red is the flap drag polar curve, and blue one is the takeoff configuration. So using this, so let's study the maneuverability of this aircraft. Okay, and also the engine information is given. So I think this is copied from Wikipedia. So this aircraft, as I said, has 4 engines, and they are turboprop engines. The engine power is given. So this is the maximum power at sea level, and there are 4 of these engines. So you need to multiply this with 4, and you need to use a propeller efficiency term, because not all of this power can be transmitted to flight due to the losses at the propeller. Okay. Now let's start with, let's pick up a speed. Okay, so let me choose 100 meters per second. So let's assume that a fully loaded, that means the weight is equal to W0, C-130 is flying with a clean wing, that means there are no flaps, at a speed of 100 meters per second. What is the highest load factor the aircraft can achieve? So we should directly go back to the definition of the load factor. It is L divided by weight. And since we are asked the maximum one, for the maximum load factor, we should consider the maximum. So the weight is constant, we can't change that. And for the maximum lift force, we need to use the maximum lift coefficient. Okay? So that's 1 over 2 rho V squared S CL max. And the maximum lift coefficient without flaps is taken from this data. I'm not sure if you can see that, but we should use this red curve. And the maximum is between 2 and 1.6, so that should be 1.8. Over the weight. So this is equal to 1.8. And we know everything else, right? We know the speed. We know the air density, the wing surface area, everything else is known. So from here you get a number, and that number okay, so I was trying to get to this one. So that number is this number. Well, here you have the curve, not a single point. But for 100 meters per second, the load factor is this much, about 2.87, let's say. So this is approximately equal to 2.87. So you can repeat this calculation for different flight speeds, right? So this is the speed at, so this is at V is equal to 100 meters per second. So if you want to find the maximum load factor it can achieve at different speeds, then you can this formula and you can insert different speed values. That will give you a curve, and that curve is this one. Well, the curve starts from this speed, which is 55 point something. That is the stall speed. Maybe I should have told you that one first. So if you you can find the stall speed as follows. At the weight should be balanced by the lift force, rho V stall squared S times CL max. So this is the stall speed with the clean wing configuration. If you put 1.8 here, from here you find the stall speed as about 55. Then let's consider the maximum speed. The maximum speed, for the maximum speed we need to use the maximum engine power for maximum speed. at sea level. So to find the maximum speed, we can use the power curve. This is the power required curve, and the power available curve is the red one. For the power available curve, I use the engine power, including the propeller efficiency. And let me so this is PA max with a propeller efficiency of 0.8. So that number is equal to 4 times this engine power times 0.8. That's what that number is. And for the blue curve, this is just the power required curve. And for the power required curve, I use the this drag polar curve, the red one. Okay. So anyway, the maximum speed can be found as approximately 159 meters per second. Okay, now we have a speed range for our aircraft, right? We know that the aircraft without any flaps can fly at any speed between 55 meters per second and 159 meters per second. And at each one of these speed values, we can calculate the maximum load factor it can have by using this maximum lift coefficient and the speed values. And if you do that, you will get this curve. So in other words, if you are flying very close to the stall speed, well, there's something wrong here, right? Because at stall speed, the load factor should be equal to 1. But according to this graph, it is less than 1. That means at this speed, it cannot even maintain its altitude because during steady flight. But anyway, I can check that later. If you look at the maximum load factor it can have at 100, it was 2 point something. But if you look at this graph, the load factor it can have increases dramatically, right? So if while flying at 150 meters per second, for example, it can have a load factor of 6.5 almost. And while flying at the maximum speed, then if it while flying at the maximum speed, if the pilot increases the lift coefficient to maximum value, then the aircraft will suddenly have a load factor of 8.5. It's almost like a fighter jet, right? Well, not almost. 8.5 is very close to the maximum load factor a fighter jet can have. So anyways, this just considers the aerodynamic limitations. Okay, so according to aerodynamic limitations, this is the maximum load factor you can have. Okay, but as I said in our last lecture, aerodynamics is not the only limiting factor. You need to consider other things as well. For example, let's see. So aerodynamically, the aircraft is capable of load factor of 8.5 while flying at maximum speed. Next, let's find out if the aircraft can perform a sustained level turn maneuver with load factor of 7, for example. At a speed of 156 meters per second. So the critical thing we should check now is, aerodynamically we know that it can generate that much lift force. It has sufficient lift coefficient to give that load factor. But let's see if the engines can sustain that maneuver. That means the engine should provide enough thrust force to balance the drag force during that maneuver. We need to check if the engines can so we know the engine power, right? So let's use the power. Can provide sufficient, let me say, power to balance the required power during that maneuver. So let's find the required power. The speed is 156 to the power 3, since we are calculating power, times S times CD, and the drag coefficient, we need to refer to this table. So we know that the wings is at its maximum lift coefficient, which is this point. The corresponding drag value, I think it's 0.23. So let me look at this data. Yeah, it's 0.23. Okay, so let's calculate that number quickly here in MATLAB. That's 1 over 2 times rho times 156 to the power 3 times S times CD, which is 0.23. It is this much watts. .67 times 10 to the power 7. So can the engines provide that much power? Let's find out. We know the power of the engines, right? So this is the maximum power of one engine, and multiply that with the propeller efficiency. That power number is this much. So one engine can provide this much power. Times the power what? 6, right? So to sustain a 7G turn, we need, so this is what we need, and let me divide that number with this number to find the number of engines we need to have. 31.6, 32. So obviously the aircraft cannot make such a turn because it doesn't have enough power. Okay, so if you think about this problem, aerodynamically everything seems to be fine. You can reach very high lift forces to get really high load factors. But if you start such a maneuver, then if you increase the lift force to its lift coefficient to its maximum value, the drag coefficient will reach this value, 0.23, and at that point the required power will be this much. And if you want to keep turning, if you want to complete that maneuver you start at that condition, you need to provide this much power to the aircraft, and if you use these engines you need 32 of them. So obviously the aircraft cannot make a sustained level turn maneuver at that speed and load factor. Okay. Okay, so let me now write my conclusion here. Obviously, the aircraft cannot conditions because enough power to then the question is, what is the maximum load factor so obviously if you are flying at 156 meters per second, you cannot sustain a full the maximum load factor turn. Then what is the maximum you can achieve? So for the maximum sustainable at that speed, 156 meters per second, required power should be equal to the available power, right? Maximum available power. For that, the drag coefficient must be less than 0.23. So what should the drag coefficient be? So this is how we can find out. 1/2 times rho times v to the power 3 times s times cd should be equal to maximum available power, which is this number times 4. So the only unknown is the drag coefficient. So from here we can find the drag coefficient as this time times 4 times 2, divide that by rho times S, 0.029. So that means instead of flying at the maximum lift coefficient, you should fly with the lift coefficient where the drag coefficient is equal to 0.29. So let's find out. So you should be flying somewhere here, right? The CL must be something like 0.42. So from the drag polar, CL value corresponding to CD is equal to 0.029 is approximately 0.42. Therefore, the maximum sustainable load factor is the one that corresponds to that value. And let's calculate that value. And divide it by W0. So this is about 1.83. Okay, so what is this number? So this is the maximum load factor the aircraft can sustain. So aerodynamically, it can, at that speed, reach load factor up to 7, but the engines will not allow it to continue that maneuver. And if you consider the engine limitation, the maximum this aircraft will be able to reach is 1.80 something, 83. So at this speed, at 156, so this is the maximum it can reach. Okay. So this is the engine limited load factor for that speed, and we can repeat these calculations at different speeds. So we can find out. So then, what is limiting engine limited load factor at this speed, for example, or at that speed? So the calculation will be exactly the same. So you will make this power required, power available equality, okay? And the right hand side will not change, so the engine can provide this much power, not more than that. So from that, you need to find the drag coefficient, and from the drag coefficient you go to lift coefficient, and that lift coefficient will give you the limit for the load factor. So now we can go back to this MATLAB code and obtain the full graph from there. Okay, so this is what you get. So this blue one was the maximum load factor limited by the aerodynamics, and the green one is the maximum load factor limited by the engines of the aircraft. So we calculated this value at 156. It was 1.83. So that point was somewhere here. But it turns out that the propulsion limit is higher at lower speeds. But nevertheless, you cannot obtain a load factor for a sustained maneuver again. So everything is there for sustained maneuvers. So this is the maximum load factor you can have. So, well, you can attempt turn maneuvers at higher speed, but what will happen is, for example, if you attempt this maneuver, if you want to perform this maneuver, you can increase the lift coefficient to its maximum value by increasing the angle of attack. And you can start turning, but the aircraft will start quickly decelerating, right? So the speed of the aircraft will start going down because you have the drag force much greater than the thrust force. Okay, so in that case, it will not be a sustained maneuver. But for a sustained maneuver, these are the limitations. Okay, so there's a critical point here where the two intersect. So what happens is, if you are flying at a speed less than this limit, the limiting factor for the load factor is the aerodynamics. Okay, so the aerodynamics limit the maximum load factor you can have. But if you are flying to the right of this point, then the limiting factor becomes the engines. Okay. So according to this, so you can make this conclusion. If somebody comes to you and say that I'm very rich, I want a C-130 aircraft to be able to make 7G maneuvers. You're an aerospace engineer, just modify this aircraft and give me a 7G capable C-130. Then you will go back to these calculations and you will say that, okay, if you want to sustain those maneuvers, then you need much more power and you need to have strong enough engines. Obviously, you cannot fit 32 propeller engines on that aircraft. But by installing, for example, jet engines, more engines that can give more thrust, you can make that C-130 perform 7G maneuvers according to these two limitations. Okay? Any questions? So when you look at the exam questions, you will find out that I ask you questions like this. For example, I give you a speed. And for example, I tell you that I give you some information for an aircraft, and I ask you, for example, what is the maximum load factor this aircraft can sustain at 70 meters per second. So you need to check two things. You need to check both of these, and you need to use the lower one. Okay. So for example, you will say that if I use engine power as the limit, then this is the maximum load factor I can have. But if I use aerodynamics as the limiting factor, then this is the load factor. And since this is the lower one, you should say this is the real load factor limit. Or if I ask you to repeat the same calculation at this speed, for example, you will again do the same. You will check the load factor limited by the engines and the load factor limited by the aerodynamics. And again, you will say that lower one of those two numbers will be the actual load factor limit. Okay. So these are the two limiting factors, aerodynamics and the propulsion, but these are not the only ones. there's one more limiting factor, and that is the more important one, and that is the structures of the aircraft, because the wings are capable of carrying only a limited amount of force, and even, for example, at this level, so you say that aerodynamically you are fine, the engines can give you this much power as well. So let's find out the how much lift force the engines should create at that level. So the load factor here is about still less than 3. Let me find a more accurate number. It is 2.86. So the lift force should be 2.86 times 1.5 million newtons. Okay, but the wings are not that strong, then you shouldn't perform that maneuver either. Even if your aerodynamics are good and the propulsion systems are strong enough, but if the wings are not, then you shouldn't really attempt that maneuver. So there's a third limiting line on the VN diagram, and that is due to the structures, and that is a flat line. Okay, so you know W0, and if you design the aircraft to withstand a maximum load factor of 2, for example, then there will be a flat line here, and that will be the limiting factor. Okay, so you shouldn't go over that line, otherwise the wings will be under heavy load and they may eventually break. Right, so remember the wing test videos I showed in our last lecture. Okay, so this is the so-called VN diagram. So the horizontal axis is the flight speed, the vertical axis is the load factor, and there are 3 limiting factors: the aerodynamics, which is the blue one, the propulsion, and the structures. Usually the situation is as shown here. The structural limitation is more important than the engine limitation. Okay, so you cannot really achieve the maximum load factors your engines can sustain due to structural limitations. These are all the same things. So in VN diagrams we have the structural limit, multiple lines for structural limits. So this is the design limit. So that is the maximum the aircraft was designed to carry. And as we saw in the previous video, usually they put a 50% margin of safety, and the wing is not supposed to break until it reaches this limit. So, and this is the ultimate limit, this line here. And if you exceed that limit as well, then the wings will break. You can't really avoid that. So if you are a pilot, you should really be very careful about these limits. Okay, so we have just 2 minutes left, and so let me just end today's lecture with a video. Okay, so suppose that you have an aircraft, and this is the flight envelope of your aircraft, and you're flying at this speed. Okay, you're doing a steady flight with a load factor of 1. So you're flying at this point, and you want to perform a maneuver. So you bank the aircraft first, and while banking the aircraft, you increase the angle of attack by using the elevator, so that the altitude will not be changed. And while doing that, you will be increasing the load factor, right? But if you give too much elevator input, then the angle of attack will be increased too much, and too much angle of attack will give you too high lift coefficient value, and that lift coefficient value can put you into this dangerous area. So if you are in an aircraft flying relatively fast, you should never give too much elevator input, because that elevator input will give you a very high angle of attack, and you can easily damage the wings. And let me show you a video for that. So this is a real video. I don't know when this was recorded, but this was during an air show, and the pilot was supposed to do some aerobatic maneuvers, I guess. But for whatever reason, he couldn't calculate the amount of elevator, the maximum amount of elevator he should give, and he attempts a high load factor maneuver, and the wings eventually break. So if you watch carefully, you will see that just before the wings break, the nose of the aircraft goes up, right? As the aircraft nose goes up, the angle of attack increases, and that increases lift force dramatically. And I was reading about this accident. If I remember correctly, this was not a high performance aircraft. It was designed for the maximum load factor of 2.5 or so. But the pilot attempts a 6-point-something G maneuver, and obviously that is much higher than the structural limit. And both wings of the aircraft just break in the air, and unfortunately the aircraft crashes. Obviously, without any wings, it cannot fly. Okay, any questions? So this is the VN diagram, and normally in practice this propulsion limit is not that important, because as I said, it is usually above the structural limit. So before you need to worry about the propulsion limit, you need to worry about the structural limit, so you don't really go there. But in exam questions, so I usually ask about these things. So just remember this example, and you should remember that there are two limiting factors. So if I ask you to find the maximum load factor for a sustained maneuver, you need to check both of these limits, and obviously you need to check the structural limit as well. For example, I ask questions like, what is the maximum load factor, and what happens if the pilot tries to reach a higher load factor? Then the answer to that question depends on where you are. So if you are here, and this is the maximum load factor, you will say that if the pilot attempts a higher load factor, it will stall, right? Because it will try to reach a higher lift coefficient, but it won't be possible. It's already at the maximum lift coefficient, so the aircraft will stall. But if you are flying here, so let's not worry about this yet. So if you are flying to the right of this level, then the maximum load factor is this much. And if I ask you what happens if the pilot tries to reach a higher load factor, the answer will be it will not stall, because aerodynamically there's still some CL value it can gain. But this time the aircraft will start decelerating, right? The aircraft will start slowing down, because the engine will not be able to balance the drag force. Okay? And if there's a structural limit, and that is the limiting factor, then you should say that if the pilot tries to reach a higher load factor, then the wings will be damaged. That will be the answer. Okay? So let me stop here. So in fact, we completed the topics of the course, except for the pull-up and pull-down maneuvers. So I explained this load factor for the level turn maneuver. So on Tuesday, I can explain the pull-up and pull-down maneuvers, but they are very similar, and there's really nothing much to say about that. So probably it will not take 2 hours on Tuesday. So on Tuesday, I will explain pull-up and pull-down maneuvers, and then maybe I can do a review for the course, or if you have any questions, we can discuss those questions. Okay? Okay, so then let me stop here, and I will see you next Tuesday.